Hey everyone! Today we're going to be talking about related rates, which is another application of the derivative. Related rates is exactly what it sounds like. You're going to have more than one rate of change, and they're going to be related somehow. So let's dive in with an example problem. We'll do another example problem, and we'll talk about how we can solve problems like this in general. So the first problem we have here is you're standing 50 feet from a model rocket launch. When launched, the rocket travels up at a constant rate of 5 feet per second. How quickly is the distance between you and the rocket changing when the rocket is 100 feet in the air? So, the first thing that I want to do is I want to draw a picture so that I have a better sense of what's happening here. So in my picture, here's me. I'm hanging out. The rocket launch is 50 feet away from me, so I'll label that with 50 feet. The rocket is going to be launched at a constant rate of 5 feet per second, and it's traveling straight up. So it's going straight up, at 5 feet per second, not 50. And then, how quickly is the distance between you and the rocket changing when the rocket is 100 feet in the air? So in addition to this moving up at 5 feet per second, this high point here is 100 feet above the ground. That's where my rocket is. And the last piece of information is the question that it's asking here. How quickly is the distance between me and the rocket changing? So this is what I need to figure out. So first, I'm going to add to my picture the distance between me and the rocket. Well, it can be represented by this straight line here, connecting me to the rocket. That I don't know what it is, and I need to find its rate of change. So, let me call this R. Okay. We can see here that since the rocket gets launched straight up, and I'm standing 50 feet away, the ground is nice and level, we have a right triangle here. That means that R, this distance between me and the rocket, well, I'll just use the Pythagorean theorem. So R squared has to be, in general, x squared plus y squared. That means that R squared should be 50 squared plus 100 squared. Which means R squared should be 50 squared is 2,500, 100 squared is 10,000, so this is 12,500. And taking the square root of this, and pulling out a nice common factor, I will get that R has to be 50 times the square root of 5 feet. Great. Now I'll just leave that there, so that it's a nice exact answer with no rounding. So now I know that my R is 50 root 5 feet. The question, though, is asking how quickly is R changing, right? This word changing tells us that I should have a rate in mind, and to find how quickly something's changing, I think, oh yeah, that's a derivative, right? Derivatives tell us rates of change. So what I'm going to do here is I'm going to take this equation that I know for sure, and I'm going to differentiate it. Now, it's important to realize that R is not just changing with respect to x, and it's not just changing with respect to y, it's actually changing with respect to time. So depending on how long the rocket's been in the air, this distance will change much more quickly at first, and then will kind of slow down in how quickly it's changing. So when I take the derivative here, R, x, and y are all functions of time, because they're all changing somehow. So to take the derivative, I'll have to use the chain rule here. The derivative of r squared is 2r times dr dt. Okay. The derivative of x squared is 2x dx dt. And the derivative of y squared is 2y dy dt. Oops, got a little cut off there. 2y dy dt. Great. So, I am in business here. What am I looking for? I'm looking for how quickly the distance between me and the rocket is changing. That's this distance here, so that's dr dt. I'm looking for dr dt. That means I should know r, x, dx dt, y, and dy dt in order to solve this. So let's just start plugging things in. I know that r is 50 root 5. dr dt. X is 50. Well, we haven't labeled dx dt anywhere in this picture. But if we think about it for a minute, we realize that since the rocket's going straight up, this horizontal distance isn't changing at all. It's just 0. So x is 50, but dx dt is 0. That means 2x dx dt is also 0, plus 2y dy dt. Well, y is 100 because I'm at 100 feet, and dy dt is how quickly I'm moving up, which in this case is 5 feet per second. So I'll get 2 times 100 times 5. And tidying this up a bit, I get 100 root 5 dr dt should be equal to 1,000. And then I'll just solve for dr dt by dividing both sides by 100 and then root 5, and that should get me dr dt. Well, 1,000 divided by 100 is just 10. 10 divided by root 5, and maybe I'll rationalize that a bit, and I'll get 2 square roots of 5, and my units are feet per second. If you want to round this, you can, but we don't have to here. 2 root 5 is going to be the exact answer. Okay. So what we did here, to just summarize quickly, we read the question. We highlighted the things that we knew and drew a picture to give it context. From our picture, we labeled everything that we knew based on the word problem. And we wrote down any equations that we could come up with that relate things together in the picture. This is the key point here, right? Everything in our picture should be related. That's why it's called a related rate. And so once we have that relationship down, the rest of the algebra and calculus shouldn't be terribly tricky, as long as we keep in mind the context of the problem, right? Recognizing dx dt is 0, even though it didn't say it, it's understood because this is always going to be 50, no matter how high the rocket goes. Okay? So we're going to move on to another problem now, and we're going to do actually the same exact scenario, but with a different question. So let me just erase all of this. Let's say if instead of asking how quickly the distance between me and the rocket is changing, I ask something like, how quickly is the angle of elevation changing? Again, when the rocket is 100 feet in the air. Well, I can figure this out too, and in this case it's nice because I already have the picture drawn here. And so it's the same exact moment in time. I just need to label the angle of elevation, which is right here, and I'll call it theta. Now I want to find how quickly that angle is changing. So my goal is to find the derivative of theta with respect to time, or d theta dt. So I somehow need to write an equation that relates theta to some of the other pieces of information I have here. And I can do that just fine. Because we solved a bunch of other things, we know dx dt, dy dt, dr dt, and x, y, and r. We could use any trig function we like. Let's say I hadn't done part A of this question and found all of the r. I'd only have the x and y's, and so maybe I'll just use tangent of theta, which is equal to y over x. Okay. Great. So first, I need to think about what is the value of theta at this particular moment in time. Just like last time I found what is the value of r at that particular moment in time. And to do that, well, I know y is 100, I know x is 50, so theta is just inverse tangent of 100 over 50, which is 2. So theta is arctan of 2. And if you want to put this in your calculator, you can. You'll get some value slightly more than 1, but you don't have to. Okay. Next, we recall that this is a related rates problem, so we probably need to take a derivative. Here you have two options. Since we're trying to solve for d theta dt, we could take this, solve it for theta, and then take the derivative of both sides. Now, I'm not going to do it this way only because doing it that way requires me to take the derivative of an inverse trig and use the chain rule, something that I don't really want to do. But I know the derivative of tangent, and I'm more familiar with it than I am with the derivative of arctangent, and so instead, I'm just going to go ahead and take the derivative of everything right now. So doing that, the derivative of tangent theta, well, derivative of tangent secant squared of theta, and then remember theta is a function of time, so I have to multiply by d theta dt. Y over x needs the quotient rule. So I need to use the quotient rule here, but that's okay because we remember the quotient rule. It's the bottom times the derivative of the top, x times dy dt, minus the top times the derivative of the bottom, y times dx dt, all over the bottom squared, all over x squared. And now we're in business here. So let's just plug in some values and see what happens. Theta is arctan of 2. If we remember that secant squared is 1 plus tan squared, then we'll get 1 plus tan of arctan of 2 squared. Tan of arctan 2 is just 2, so secant squared of theta is just 1 plus 2 squared, or 5. Now there was a lot of math that I just kind of talked out loud with the trig identity here. If you want to write that down, you can go ahead. But also, if you wanted to approximate the value of theta here, you could then plug that into a secant squared in your calculator and you should still get 5 out for your answer. We know that x is 50 feet, so x is 50. dy dt we know is 5, minus y is 100. dx dt, we remember, is 0 from the last portion, but again, right, if you didn't remember that, how quickly is x changing in this case? It's not changing at all. I'm not moving closer to the rocket's not moving at an angle, it's just moving straight up, so dx dt is still 0, and then I'll divide this all by x squared, which is 50 squared. So let's see here then, d theta dt. Well, this is just 0, 50 over 50, that'll cancel, leave me a 50 in the denominator. 5, divide that by 5 will just give me 1, so I'll get 1 over 50. And my units should be radians per second. So that's how quickly my angle is changing in this case. Okay. Again, I did do a lot of hand-wavy, let me talk you through the algebra to get to this simplified answer. It might be in your best interest to make sure that you can do all of the algebra on your own rather than taking my word for it. Same with the trig identity up here. But again, the procedure is exactly the same. We start with some word problem here. We read it, we understand what it's asking for, we understand the scenario, we draw our picture that gives context to the scenario, we label it with everything we need, we determine the relationship between the rates, sorry, not just between the rates, but between everything in our picture, which then leads us to a relationship between all of the rates, and then we plug in everything we know to solve for the desired rate. Okay. So those are just 2 examples that I did. This third example, I'm actually going to pull from your textbook. So if you could, at the bottom of page 247, example 3 outlines a particular car chase that is happening. So you can follow along with that example as I go through it, or you can just listen as I read it to you and then draw a picture and proceed to solve the problem as we've done with the other 2. So, here we go. A police cruiser approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. When the cruiser is 0.6 miles north of the intersection, the car is 0.8 miles to the east. The police determine with radar that the distance between them and the car is increasing at 20 miles per hour. If the cruiser is moving at 60 miles an hour at the instant of measurement, what is the speed of the car? Wow, okay. Lots and lots and lots of words there, but that's okay. I'll start just by drawing a picture here, just like I always do. So here's an intersection. Now the first thing it says is the police cruiser is approaching this intersection from the north. So my police cruiser, maybe I'll label it PC, is up here at the north. Okay. Next, it says the car has turned the corner and is turning straight east. So the car has turned the corner going east. So this is east, and there's my car. Okay. It then gives me some measurements. The police car here is 0.6 miles, and I'll just write that with MI, to the north of this intersection. The car is 0.8 miles to the east of the intersection. And it gives us the rate at which the distance between them is changing. This distance, again, I'll call this r just like I did before. It tells us that dr dt, the rate of change of the distance, has to be 20 miles per hour. It also tells us the police are approaching this intersection at a speed of 60 miles per hour. And the question is, find the speed of the car. This speed, we don't know. Okay. So, let's write our equation down. Again, we have a right triangle, so we can always write down the equation r squared is x squared plus y squared. That's always true with a right triangle. Now, we don't know r. We do know x and we do know y, so we can solve for r. If you look, y is 0.6, x is 0.8, so maybe we recall 6, 8, 10 right triangle, but if not, we can go through and solve. This is 0.8 squared plus 0.6 squared. 0.8 squared is 0.64, 0.6 squared is 0.36, add them together you get 1, so r squared is 1. That means r is 1 mile. Oops, not miles. So r is 1 mile. Great. And then the last thing we need to do, since we're concerned about the rate of change, right, the speed of the car, we need to create an equation that relates the rates to each other. So again, we'll do that. Take the derivative of everything. Remember, all three things, r, x, and y, are functions of time. So when we differentiate them, we have to use the chain rule. So we get 2r dr dt has to be equal to 2x dx dt plus 2y dy dt. Now let's start plugging some things in. We know r is 1. We know dr dt is 20. We know x is 0.8. We're looking for dx dt. We know y is 0.6. And we know dy dt is 60. So we know every single thing in this equation except for dx dt, which is great, because that's what we're trying to solve for. So let's just start plugging in. I get 2 times 1 times dr dt, which is 20, should be 2 times 0.8 dx dt, which is what I'm trying to solve for, plus 2 times 0.6 times dy dt, which is 60. And now we'll simplify and do some fun things. This is 40, and that should be equal to 2 times 0.8 is 1.6 dx dt, plus, okay, 0.6 times 60 is 36, times 2 is 72. Okay, and then, if we subtract our 72, we'll get negative 32 is 1.6 dx dt. And that would make dx dt, oh, let's see, 1.6 into 32 is negative 20. Now, I'll label this with miles per hour. Here's the deal. I've intentionally done something wrong here. So let's figure out what I've done wrong, and then talk about why it's wrong. You should notice that negative 20 miles per hour doesn't make a whole lot of sense in this case, because a negative 20 would mean that I'm moving to the left. That's bad because this car is moving to the right. So apparently I have overlooked something here in my original solving of this problem. Now, what have I overlooked is the question. Well, r is a distance, so r can never be negative, so that seems fine. But you'll notice that my police car is actually getting closer and closer and closer to this intersection. It's moving down. So if I'm just concerned about the intersection and the distance away, this distance is shrinking. So that means the velocity here, since it's going down, should be a negative. My dy dt shouldn't be 60 miles per hour. It should actually be negative 60 miles per hour. Okay? So here where I had 60, I really should have negative 60, making this negative 72, which makes this positive 112, making our final answer 70 miles per hour. Now this should make a lot more sense for two reasons. Reason one, the car is moving to the right. We should get a positive answer. Reason two, the car is speeding. The whole context of the problem is about a speeding car. Saying it's going 20 miles an hour doesn't make a whole lot of sense, but saying it's going 70 miles an hour makes some good sense. I hope that this intentional error that was built in helps you to be a little bit more aware of the importance of checking your answer and being able to figure out where we went wrong. Again, the procedure was we read the problem carefully, we draw a picture to help us give context, we label everything we know in our picture, we then write down the equation that relates everything together in our picture, we differentiate it to find how the rates are related to each other, we solve, and then the important step that we hadn't been doing in the previous questions has been checking our answer for context. Make sure that it makes sense. In this case, negative 20 miles an hour didn't make any sense, but 70 miles per hour makes much more sense. All right, thanks for watching.